In the last video, what we found was when we looked at the specific volume of steam at these conditions, 4,000 kilopascals and 300 C, we looked at it how we have typically done in the semester using Cat 3. We found that the specific volume was 0.05884 meters cubed per kilogram. And we went and calculated this with the ideal gas law and found that the value we calculated was 0.0662 meters cubed per kilogram. In this video, we're going to look a little bit into why these values are different and what we can do about it. The value that we got from Cat 3, the 0.05884, that value is the true value, how much space a kilogram of water takes up, 0.05884 meters cubed, about 5.8 liters. So that's how much space a kilogram actually takes up. And what we're looking at here in the ideal gas is how much space a kilogram would take up if this water, again, it's steam and water vapor, if this acted and behaved as an ideal gas. In this case, it would take up, again, 1 kilogram would take up about 6.6 liters. So 5.8 liters to 6.6 liters. The question is, why are these values different and what can we do about it? These values are different. The ideal gas law gives us about a 12% error. With PV equals RT. So they're clearly different. We can look at why they're different, right? The 6.6 liters, that value, this is 5.884 liters per kilogram. Just so that it's easier to talk about, 6.62 liters per kilogram there for the ideal gas. So the 5.8 liters per kilogram, that's the true value. Ideal gas assumed that it was, or calculated that it was 6.6. So why are these different? They're different because our real gas molecules attract each other. So let's think about what's happening. An ideal gas under these conditions would take up about 6.62 liters. Ideal gas means that the molecules themselves don't take up any space and that they never see each other. They don't interact at all. So they never feel any other molecules in the system. The real system, on the other hand, is a little bit smaller. So it's actually like all of the gas molecules attract each other enough, which makes everything shrink in and get pulled together just a little bit, which gives us about a 12% error. So the reason that these are different is because of this molecular attraction. So now the question is, what are we going to do about it, or what are we going to do differently to be able to model real gas behavior? So ideal gas law, that works fine if we have an ideal gas, but if we have something that's not ideal, like we have in this case, how do we handle that? So one fun way to do that is just by adding a fudge factor. We'll call that fudge factor Z. So we can now write a new equation relating pressure, volume, and temperature. PV equals Z RT. Where, okay, so what is the value of Z? It's some number which helps us get the right answer, right? It's a fudge factor. So Z would be defined as PV over RT, which in this case would be 0.8893. Right, so if we use this new ideal gas law equation, P PV equals ZRT, and we use a Z value of 0.8893, we get the right answer. Now, you may be looking at this and saying, well, that's all fine and dandy, but how do we find Z? Okay, we'll get there, but let's first talk a little bit about what Z means, because there's actually some physical insight that we can gain by looking at this compressibility factor. Okay, so that's what we call this, this fudge factor, Z. We call it the compressibility factor. When Z equals 1, that means our system is behaving as an ideal gas. Z equals 1, then it's just PV equals RT, the ideal gas law. If Z is less than 1, which was the case for our example, that means that the real gas takes up less space than the ideal gas. Which means that there are attractive forces which are pulling the gas molecules together. If Z is greater than 1, that means the real gas takes up more space. So that means that there are repulsive forces which are pushing the individual atoms and molecules of the gas, pushing them apart. So if Z is 1, that means the ideal gas law assumptions must have held, because we have a system where we are behaving as an ideal gas. If Z starts deviating from 1, if it goes less than 1 or more than 1, that means these ideal gas assumptions, molecules take up 0 space and they don't interact with each other, those two assumptions start breaking down. So when does that happen? The ideal gas law assumptions are going to break down when molecules do start to see and feel each other, and when their volume is important in the total volume of the system. So that's going to be happening at high pressure. It's going to be happening at low temperature. High pressure, I think, is fairly easy to understand. Low temperature might be less so, but if we think about it, high temperature gas molecules are going to be moving very quickly. And if they're moving fast, right, they don't have time to stop and feel an attractive force from a neighboring gas molecule, because the two just whiz right past each other. If they're going slow, they just are kind of meandering by each other, and they're going slow enough past each other that they do have time to feel the neighboring gas molecule and be attracted, for example. So high pressure, low temperature, and the other one is low specific volume. Right? If the volume is low enough that, again, the gas molecules are close together and they start to feel each other and they start to take up an appreciable amount of space. So this is when our ideal gas law assumptions break down, but I kind of have just hand wavy, I guess, type statements here. High pressure, low temperature, low specific volume. What does that actually mean? So we'll take a deviation over here to some phase diagrams. So if we think about phase diagrams, as we're thinking about what these mean, here's just a general phase diagram, and I'll just point out some key features of it. Right, all phase diagrams have these general features. They have a solid, liquid, vapor portions of their phase diagram. They have a triple point, which is down here, which is where you can have an equilibrium between solid, liquid, and vapor all at the same time. So you can have ice and liquid water and boiling all at the same time, which is kind of crazy. So you have ice water that's boiling. You can have that at the triple point. The other point that you have that we've spent a lot of time dealing with is this line here, the line between the liquid and vapor regime. So this line here, that's the line where boiling occurs. That's going to be the line, right? We looked that up in our table. That's kind of in the first two sections of our steam table, where we have liquid and vapor we have boiling and condensation happening. The other point that we have here is the critical point up there. So the triple point, and really the critical point especially, kind of anchors the this saturated curve, the liquid vapor curve. It anchors that in pressure temperature space. So it says kind of where that curve is. If we think about the ideal gas law, okay, when are the assumptions going to be valid and when are they going to be not valid? They're going to be valid if we're somewhere, say, like anywhere over here. Think about why. Well, they're going to be valid because we're right down over in this region over here, the lower right-hand region, we're going to have gas molecules which are at low pressure and low temperature. As we start to move closer and closer and closer toward that way, toward this liquid vapor curve, that's where gas molecules are going to start to feel each other. They're going to start to feel the presence of other molecules in that vapor phase. Right? A liquid is where the gas molecules really feel each other a lot. They feel attractive forces so much that they get stuck together and turn into a liquid. So as you get closer and closer and closer to that liquid phase, as we go along here and get closer and closer and closer to the liquid, we're going to be starting to feel attractive forces and become less and less and less like an ideal gas. Let's look at water's phase diagram. Here's water's phase diagram. It has a triple point. It has this same vapor-liquid curve. This would be the vapor-liquid curve that we look up in steam tables, and it has a critical point. It also has some fun stuff going on up at the top with different kinds of ice. We don't talk too much about solids in this class, but you have actually different crystal structures of ice which are favored at different temperatures and pressures. Some kind of fun stuff. But it has the same general features. Okay, we took pressure on the y-axis and we changed it to a log scale so we could see a huge range in pressure. But it's the same thing. We have pressure and temperature. On this phase diagram, right, being down here in the bottom right, that's going to be where we're ideal gas. As we get closer and closer to this vapor-liquid line, that's where we're going to be deviating from ideal gas. Let's look at carbon dioxide. In a totally different substance, but the phase diagram looks at least ballpark the same. We again have a critical point up here. We have this vapor-liquid line here. We have a triple point. But as we're down here in the lower right, that's where we're going to be at high temperature and low pressure. And that's going to be where we are ideal gas. As we get closer and closer to this line, we're going to start deviating from the ideal gas law. So there are a couple things that we can say. The critical point is the end of the saturated vapor-liquid curve. That's supposed to be a V and an L, the vapor-liquid curve. So it kind of anchors that vapor-liquid curve, and it defines where the phase change occurs in pressure temperature space. So we're going to most often be interested, right, high pressure, low temperature. What is high pressure and low temperature? Well, the critical point can help us understand that. So the critical point happens at a set pressure and temperature, right? It's a point on this pressure temperature phase diagram. We call that the critical pressure, the critical temperature, and we can check our pressure and temperature against these to kind of see, are we in this region where we're low pressure, high temperature? We can kind of use these as a check of the ideal gas law assumption. So if the pressure is much less than the critical pressure, that means our pressure is low. And if the temperature is much greater than the critical temperature, that means the temp is high. Right? So these things that we wrote here, when do the ideal gas assumptions break down? Because this is the flip side of that. When do the ideal gas law assumptions hold? They hold at low pressure and high temperature. So this is when the ideal gas law assumptions hold. We can check this quantitatively using what we call reduced temperature and reduced pressure. These are just the temperature over the critical temperature or the pressure over the critical pressure, right? Are we 10% of the critical pressure? Are we 5 times the critical pressure? Are we 10% of the critical temperature, 5 times the critical temperature? So it's just a dimensionless quantity that tells us in relation to the critical point, where are we? And the physical insight that we have is that each substance while different, obviously each substance is different, behaves similarly at similar parts of the phase diagram. Which by this we mean similar reduced pressure and reduced temperature. If we're in a similar spot on the phase diagram, we expect to behave similarly. And that's kind of the interesting physical insight that we have. We can use that to then model real gas behavior based on even a system that we don't know, based on systems that we do know, or measurements that we have taken before. So this is the most basic real gas model. There are lots of other ones. In engineering thermodynamics, you really will dive into, if you take that, if you're a chemical engineer, if you take more thermodynamics, you'll really dive into what these different models are and how we can model gases at all different temperatures and pressures and all different kinds of molecules and all of these things, right? Start to actually incorporate strength of molecular interaction and physical size of the molecules, incorporate some of these things into the model of our gas. We're going to stick with this model, the compressibility factor, because there's actually some interesting things going on, right? We can see directly from the value of the compressibility factor, as we've shown here, what kind of interactions are dominating, which is a useful thing to be able to see and get some sense of physically what's happening and why. So we can do that. This is a handout that hopefully you got in class. Otherwise, you can find this on Moodle and print it out. This is what we call the compressibility factor chart. And how we're going to use this chart is we're going to use this as our predictive tool to be able to figure out what the compressibility factor is without knowing the right answer, right? That was the problem that we had at the beginning. We could find what the compressibility factor is if we already knew the answer. This helps us to find compressibility factor without knowing the answer to start with. So this we can use because different gases behave similarly. We can use this for all different types of substances. Now that's a generalization, that's not exactly true, so this will introduce some error. We'll look at some of that in some of the homework that we're going to do. But essentially what we're going to do is calculate the reduced pressure and reduced temperature. Say we calculated a reduced pressure of 1 and a reduced temperature of, say, 1.5. So PR equals 1, TR equals 1.5. We would find 1 on the x-axis, and then we would carry that up until we crashed into 1.5. Right, all of these little crazy lines there, those are all reduced temperature lines. And then we could carry that across to here on the y-axis and say that our compressibility factor, Z, was about 0.91. So we can read off what our compressibility factor is from a chart like this. As long as we know the reduced pressure and reduced temperature, we can find those from the critical constants. This last table, again on Moodle, is critical constants for a whole bunch of different substances. So for example, down here is water. So water has a critical temperature of 647 Kelvin and a critical pressure of 22.1 megapascals. So what's low pressure for water? Well, less than 22 megapascals. What's high temperature? More than 650 Kelvin. So actually quite high. Some other substances like helium. Okay, helium has a temperature of 5, or a critical temperature of 5 Kelvin. So what is high temperature for helium? So really high temperature for helium might be, negative 250 Celsius. If you're helium, negative 250 Celsius is still really, really hot. If you're water, that's pretty cold. If you're anything else, that's pretty cold. But if you're helium, negative 250, you're still nice and warm and toasty. So you can see kind of, if you just glance up here, the range that these different values can take. We have the critical temperature, the critical pressure. There's also the critical volume. Here, we'll largely ignore that, but we can do a similar types of analyses with critical volume as we will do with critical temperature and pressure. But this chart allows us to see and compare the critical points with our actual state, and then get a sense of, what is this temperature and pressure? What is this like for helium versus water versus ethane and ethyl alcohol and octane and, refrigerants and all kinds of different things. So we'll use this in conjunction with the chart above to be able to predict what the compressibility factor is and to be able to predict real gas behavior. That's ultimately our goal for what we want to do, extend beyond the ideal gas law to be able to predict real gas behavior.